Hello all. Today I am going to start with a new topic. Like in aptitude, the most common thing is to start with number system. So in number system, I am going to deal with one concept of finding the number of trailing zeros. Suppose any big number is given, then we have to find how many zeros are there at the end. That is, how many zeros are there at the end of the product. How can we do that? So firstly, let us start with a simple thing. Like first we know that, for example, uh, 10 has a single digit. 10 has one trailing zero there. So how? If I factorize it, then I can write it as 2 into 5. Similarly, I can write 100. Next one is 100, which has two zeros at the end. That is, I can write 100 as 4 into 25, or I can write 4 as 2 square into 5 square. Similarly, 1000, I can write it as like 8 into 125, right? So that gives me, I can write 8 into 125 is 1000. So I can write 8 as 2 cube into 5 cube. 125 is 5 cube, 25 into 5 is 125. So this procedure, this procedure continues for any number. Like suppose now we can with this we can assume that if n is a number of trailing zeros, number of trailing zeros, we need exactly how many combinations. So we need exactly 2 power n cross 5 cross n, or n combinations of, I can write it as n combinations of 2 into 5 products. So I can let me take it off. Like I want to express, I mean that we want to express any number in the form of 2 power n into 5 power n, so that that will give the, if this product will have 10 power n, like is equal to 10 power n. So there are n number of trailing zeros, right? So this is the logic we are going to use to solve the questions. And also, so this is the thing. So firstly we need n combinations of 2 into 5 products. So we are going to find out what happens. So let me start with a simple example first. Like the first one is, let me tell the factorial, 10 factorial. Now I hope that everyone are aware of what is factorial is. Like the factorial is nothing but, if I write n factorial, that is n into n minus 1, n into n minus 2 up to 1. So this will go on. So for example, 10 factorial is nothing but 10 into 9 into 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1. So there is 110 here. Straight away 1 0 is there. I want to find number of trailing zeros for 10 factorial. So there is 1 0 already. So I'll write 1 here plus something else. 9 is there, 8 is here, and also 4, 2, and 1 5 is there. So you know that I need combinations of 2 cross 5, but there is only single 5 here. So what I can do is there is only single 5 here. So how many ever there are 2's doesn't matter. Now 8 and 4, this is 2 power 3 and 2 power 2. But you can see that there are so many 2's, but there is only single 5. So we can have only single product of 2 cross 5. So single product of 2 cross 5, that's all we can have. It is limited due to only there is only one 5. If there is other 5, then maybe we can use this 4 or 8 to split into 4 as 2 into 2 and do it. But there is only single 5, so I can write this as there is one more 0, that's all. 1 0 is due to this 10, and then other trailing 0 is due to 5 cross 5, 2 into 5, that is 10. So it will give a 0. So totally there are two trailing zeros. So this is the concept, like how this is a simple, very simple example. Not every time you have to. And now you'll ask me, I mentioned, how to find. There are, if there are so many twos. Let me continue with this example. Now let me take one more example here. So if I take one more example, like say question is 2 power, let me take 10 into 5 power 21. So if I take how many number of zeros are there, find the number of trailing zeros. Trailing zeros, how we'll find? Now, as I mentioned, you have to find the number of 2 cross 5 products in this number. So I want to split this 2 power 10, I'll keep as it is, but there are only 5 power 10. I can write this as 5 power 10 into 5 power 11. So there are only 10 5's and 10 2's, multiplication I'm talking about. But these additional 11 5 products doesn't add to any trailing zero. As you got my point, this one, this 11 additional products of 5's doesn't add to the number of trailing zeros. So there are only 10 trailing zeros for this product. So now we can simplify this, and general expression can be like, suppose there are, if 2 power x and into 5 power y, then the number of trailing zeros, this is a product, the number of trailing zeros is number of trailing zeros is given by minimum of what, x and y, the powers of 2 and 5. So here the minimum is 10, so obviously the trailing zeros is 10 only, so that extra 11 doesn't contribute. So this is one more concept to solve the question. And now the main thing is, as the questions, these are very simple problems, but the question, sometimes the number may be very big. For example, if I want to find the number of trailing zeros in 76 factorial, obviously I cannot write 76 into 75 into 74 into 73. I can write, but this is not at all method to do it. It will take 10 minutes maybe, or more than that, to solve this, or maybe even 15 minutes is not sufficient. This is the most inefficient way if we try to solve that manner which we did, like how we solved the 10 factorial one. Then how we are going to find the number of trailing zeros? Now there is one concept here, that is calculating the highest power of a number. of a prime number, not any number, but prime number in a factorial. So how we do this is, let me assume this prime number is p, and then the factorial is n factorial. The number is n, and the factorial is n factorial. Then there is one method, highest power is given by highest power is given by uh, this is the greatest integer function of n by p plus n by p square, and this n by p cube goes on till 0. This will go on till how many ever there, but most of the cases these three are sufficient first. But we are still not going to use this one, as let me give one example. To this bracket represents the greatest integer function. Greatest integer function. So what is greatest integer function? For example, if I take a number x, the greatest integer function, if I represent like this, I want to find the greatest integer function of, say, there's a number 2.3. What is the greatest integer function? For 2.3, I can write as greatest integer of 2.3. I can write as you can see that 2 is integer and 0.3 is a decimal part of it. So 2 is the greatest integer here. This output of this function will be 2. Similarly, if I take one more example, like you may think more than 0.5, or it is not like that. For any number, positive number, if I take 2.9 also, the 2.99 also, the greatest integer function output will be only 2. So why I am saying this is, like, this is important here, because we are using here, but still anyways we are not going to use it. No, but you have to know, you have to go by first conventional method, then only know the shortcut. So this is a conventional method. This itself is a shortcut, right? So now let us solve and one more question you may ask, like, not needed, so I'm not telling it right now. I'm going to solve the number of trailing zeros in 76 factorial. So as you know, 2 and 5 both are prime numbers. We have to find the highest power of 2 or 5. As you know that 2 is a smaller number, so we have to find the power of 5. 2 is a smaller number, so there can be many 2's, but only very fewer 5's in a product. Obviously, in a big number, the number of prime factors, 2 may be highest compared to 5. So we assume this is a, so let me take an example again. As you saw in that 10 factorial example, let me use that old one. So there are so many 2's here, like 2 power cube, 8 is 2 cube, and even 6 is 2 into 3. Any number, there will be so many 2's whenever an even number is there. So we have to limit the number, but we will have no use if we find the highest power of 2. We have to find the highest power of 5, because that will be minimum always. So what you are going to do is to find the highest power of 5. So if we find the highest power, and one more thing we have to check is that this 5 is a prime number. This is a prime number. Even 2 is a prime number. So if I want to start with the highest power of 5, I'll start with n is 76 here. 76 divided by 5 plus how much? 76 divided by 5 square, that is 25, plus 76 divided by 5 cube, 125, this is 0. So this is 0. So only, as you can see here, only first two terms are there. The third term reduces to 0. So here if I start, since this is the greatest integer function, as you might understand, that we have to ignore the remainder. Well, division, 76 is not divided by 5 exactly, but 75 is divisible. So 15, 5s are 75. So similarly, 25 is also not divisible. This is what is greatest integer function does, right? 15 point something is there. So we don't want the decimal part. We are removing it. The decimal part only we are considering the integer part. So we are considering the greatest integer. So 76 divided by 25. This is going to be 3 plus 0. So totally 18. So there are 5's. Highest power of 5 is 18. So 5 power 18. So if there are more than the 2's can be 18 plus something like 18 plus x. So how many our 2's are there? It doesn't matter. So this is what you can use here. That is minimum of 18 plus something, some number, and 18. Always is going to be 18. So this is what is the concept. Trailing zeros is 18. Number of trailing zeros equal to 18. So this is what is a good example. But again, this method also seems little tedious, because write it again, divide and divide. So much time it will take. Let me take an example again to show you. I want to find the number of trailing zeros in 124 factorial. So what happens? Let me see. I'm increasing the number. 124 factorial. Now this number is even bigger. If I write, I want to find the highest power of 5. So I am going to write as 124 5 plus 124 by 25 plus 124 by 125. So this again is 0. This turning out to be 0. 5, I have to divide this. 120 is a last number. So 5, it is going to be 20, 21, 20, 21, 24. So this is 24. 24 5s are is 120 plus 25 4s are is 100, and yes, 4 plus 0. So that's how it goes. 28 trailing zeros. So you can see that the number of zeros are increasing. Yes. You might not appreciate the number, right? Because how much big number is this? 10 factorial itself is very big number. So I'm not going to calculate that one, but I'm leaving here. And I'm going to tell you one more. We don't want to use this method again, because this seems little tedious. You have to do back-to-back divisions. Say what if we... So there's one more method by long division. This like a simple division only, but what is a thing is, we'll use how we do a division we can use, but we have to consider only quotient. Remember, you have to consider only quotient and ignore remainder. Now I'll take an example of 124. So okay, let me start with say 76 first. That's what we took first. So if I start with 5 here, 5 ones are and 26, 5, 15. So that's all. I hope everyone knows the division. So 15. So 5 3s are 15. So if I multiply this 15 to 5, 75, but 1 is a reminder, but we are leaving it. As I told that we have to ignore the reminder. So that's all it is. So now 5 zeros are. So we have to add these quotients here. 15 plus 3 equal to 18. So this is the number of, and this also plus 0. So this gives me the number of trailing zeros. As you can see, this 18 matches with the way we calculated before. This is a formula base, and this one is simple division. So similarly, I can do it for 124. Let me do it. 5 124. 5 2s are 10, and 2 is remainder 24. 20. 5 4s are 20. So 4 is reminder, but we are ignoring that. Similarly, 5. Here if I take 5 4s are 20. 0 here again. So these three we have to add. 24 plus 4 plus 0 equal to 28. So I hope this method is clear. Again, here you can see this number is matching with what we did with the conventional method. But that conventional method is itself a shortcut. As you know, we started, I hope you remember that we started with the 10 factorial by simply finding the number of 2 cross 5 products. From there on, we came this long. Firstly, what happens when there are different, the powers of 2 and 5 are different. We saw what happens. We have to consider the minimum of those two, the minimum power of those two. Similarly, then we cannot keep on multiplying for a big number like 76 or say 120. We cannot keep on multiplying and find out. That is impossible. It is possible, but yeah, you need to take a lot of effort. So there is a method to find the highest power of a prime number in a factorial. This is a method, like highest power is given by greatest integer function of n by p plus n by p square plus n by p cube, etc. till on, it will go on how much ever you want. Then yes, this then using this we are finding for a big number, but again we find that we have two continuous division here. So this method also is good, but somewhere we feel that little more we can add little more simplicity to this. So they are using this division table. This method is the ultimate one. So this is the shortest method. So this is the shortest method we can use. So now we'll take one more big example. Say if I take 537 factorial. 537. 537 factorial. Simple again. You have to find the highest power of 5. Similarly, you can using this formula, not only you can find the number of trailing zeros, but suppose they ask to find the highest power of 3 or highest power of 7 or any prime number in such a big number, you can use that formula and to find the highest power. So not only related to trailing zeros, you can use it, but here I am going to consider only trailing zeros. So 5, I'll write 537 here. So how much? 1, 0, 7. And again, I am going to ignore the remainder. As you know, it is like a normal division. 5 2s are 10 and 1, 21. Similarly, I will write 5 4s are 20. Yes. So 0. So we have to add these all. 107. Don't add the number, main number. 107 plus 21 plus 4. It gives me how much? 25, 132. So these 120, 132 trailing zeros. We are only discussing about trailing zeros, so I am not writing it again and again. Let me take even more bigger number, or it is going to be bigger number only. Yes. Let me take a big number, 7. Let me take 753 maybe. If I take that, what happens? Again, you know, it is only simple division. 753, 5 ones are 5 5s are 25, 0, and 50, and 5 3s are 15, 0. This is going to be 5 6. Now 5 1s are 5. So that's all. So we are going to add 150 plus 30 plus 6 plus 1, which will give me 187. 36, 37, yes, 187 trailing zeros. So if there are any calculation mistake, hopefully you ignore it, but mostly I try to avoid any calculation mistakes here. So this is what is up to, this is a concept of trailing zeros. You can solve any big number, or say you want to find for 1000 factorial. I will end here by last example by taking 1000 factorial, 4-digit number. So now I want to take 1000. So any number you can take, it is the shortest method. This is the shortest method. 200 5s are is 1000, 40 5s are is 200. Similarly, I take 5 into 8, 5 into 1 is 5, so that's all 0. Add all, 200 plus 40 plus 8 plus 1, so 249 zeros are there. So 249 trailing zeros. So I hope the trailing zeros is clear. There is some number, and here there are 249 zeros at the end. These numbers are ended by 249 zeros. That is trailing zeros. So again, I am going to simply repeating it to ensure that you all are in line with what I am want to convey here. And I am going to bring more concepts, like for example, unit digit concept is an interesting one, which will bring in the next video. Thank you.